Okay, we're going to finish chapter 5 where we're talking about atomic structure. And so we're getting a better understanding of how we understand electrons exist within atoms. And so I will just pick up where I left off. And so let's just think a little bit here about what we're doing. So we're using calculus to come up with wave functions, and those wave functions are orbitals. They tell us where electrons are likely to be found. But what they're really doing is labeling energy levels. So remember at the start of this chapter, we talked about atoms give off characteristic wavelengths of light. So yellows, greens, blues, based on which element it is. And the light's given off when electrons go, for example, on this picture from a 2s down to a 1s. You'd get light given off for that transition. If we went from 3s down to a 1s, the light would have higher energy, therefore lower wavelength. And so what we're really doing with electron configurations and quantum numbers is trying to put labels on these energy levels. And once you put the labels on, the other thing you notice is that each of those levels, so a 2s, 2p, each of those levels has room for 2 electrons to stand on it. So it's like thinking about you're climbing up a cliff and going up in energy, and you have little rock outcrops that you can stand on. But each rock outcrop only can hold 2 people. So once you have 2 people on one, another person comes along climbing the same rock ledge, and they have to go to a different place to hang out, a different energy level. And if there are 2 electrons on the same location, so in the same orbital, then they have to have opposite spins. So electrons have spin, which give rise to a tiny magnetic field and to a spin quantum number. So what was noticed is that electrons interact with a magnetic field, and there are 2 possible orientations. So this shows the magnetic moment can be in the up direction or the down, the north or the south. And when that's true, if you have 2 electrons in the same orbital, one has to be up and one has to be down. That's called pairing them. So Pauli's exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers. And so our quantum numbers are n, l, and m sub l. And once you have n, l, and m sub l, you know which orbital it is. You know it's a 4p with a negative 1 m sub l or another orbital. And once you know that, then each of the 2 electrons you put in there, one you'll give a plus 1/2 and one you'll give a minus 1/2 for the last quantum number. So when we think about the energy levels in atoms that have more than 1 electron, the electrons are going to interact with each other. And so if we just had hydrogen, so if we just had one of these blue electrons, then it would be attracted to the nucleus, which is shown in kind of an orangish color and given the label Z because its charge depends on how many protons are in there, which is the Z atomic number. But if there's only 1 electron, it would always see that full charge of the nucleus. But as soon as you put in more electrons, then they interact with each other. And so they essentially block an electron from seeing the total nucleus. And so the actual charge on the nucleus that they see is called the effective nuclear charge, ZEFF, Z effective. And it's the nuclear charge that's actually felt by an electron. So it's only an important concept when you're talking about atoms with more than 1 electron. So it's going to be the actual charge, so the actual number of protons in the nucleus, minus how many electrons are shielding the electron you're talking about from the nucleus. And so the orbital type will help determine how much electron shielding there is. So the nuclear charge is, or the Z effective is the nuclear charge that's actually felt by an electron. So Z effective, as the last slide says, is the actual charge minus the shielding. And this just shows you that the Z effective gets larger when you're talking about orbitals that have smaller L value. So we'll talk a lot about this in class. The energy, the energy of the orbitals goes up as you go from left to right. The charge on the nucleus goes up when you go from right to left. So electron configurations of multi-electron atoms. A description of which orbitals are occupied by electrons is what an electron configuration is. When you have degenerate orbitals, that means you have orbitals that have the same energy. For example, like the 3p orbitals in a given subshell all have the same energy, so they're called degenerate orbitals. The ground state electron configuration is the lowest energy configuration, and the Aufbau principle tells you how to put the electrons into orbitals so that you are putting them into the lowest energy. And so the rules for putting them into the lowest energy are that the lower energy orbitals fill before higher energy ones. That makes sense. An orbital can hold only 2 electrons. That's what Pauli's exclusion principle says. And when they are in the same orbital, they must have opposite spins. One's plus 1/2 for m sub s, and one's minus. And if 2 or more degenerate orbitals are available, follow Hund's rule. So here's Hund's rule. If you have 2 or more orbitals with the same energy, so 2 places to sit on your ledge that have the exact same energy, 1 electron goes into each until they're all half full. And then once that's true, if you have to start pairing them, you're gonna put them into the same orbital as another electron and pair the spin. But until they're all half full, the electrons in the half-filled orbitals will all have the same value for their spin quantum number. So example for 3p orbitals, all with the same energy, you're going to put 1 electron in each, and you're either going to give each of them a plus 1/2 or a minus 1/2, as long as you just give them each the same. Then when you start putting in an electron, because you can't put them in a single one anymore, you have to start pairing them, you're going to give it the opposite spin. So this just shows you the relative energies. And what you notice is, if you look on the right-hand side at a multi-electron atom, the 4s is actually going to be lower in energy than the 3d. It's kind of subtle, but it will always be true that you'll fill the s orbital from the shell above, and then you'll come back and fill the d. So these will be rules that we use in class, and we'll practice a lot of drawing electron configurations. So for the electron configuration for something like hydrogen, the number out front to the left is the n quantum number. So the electron goes in the lowest energy n value, which is 1. The shape can only be an s, where L equals 0. And then the superscript on the right-hand side is the number of electrons that are in there. So a hydrogen atom has 1 electron, so it's going to be in the lowest energy orbital, which is a 1s, and a 1s1 shows you that there's just 1 electron. For helium, also going to be putting them in the lowest one. The s orbital is the lowest, but now you have to put 2 electrons in. Lithium, now you have to go up 1. Let's go back here. Sorry. You go here, once the 1s is full, then the next one on the left-hand side for a multi-electron atom is the 2s, then it'll be the 2p. So lithium's going to have a 1s2, but then the next electron has to go into a 2s orbital, so you're going to have a 2s1. Nitrogen, you're going to have a 1s2, 2s2, 2p3. So if you look at nitrogen, it has 7 electrons. So when you get to the p orbitals, which all have the same energy, you're going to put 3 electrons into those p orbitals, 1 into each. On the right-hand side, now we're just showing you another way to represent this, more like the ledges on the cliff I was talking about. So you have a 1s orbital, and the arrow shows you that it has 1 electron in it, and its spin is pointed up. Then when you make helium, you have 2 electrons, same 1s orbital, but now you have to have a +1 and then a -1 half spin for each of your electrons. And then for lithium, same thing, the 1s is full with 1 up and 1 down, and the 2s has to then have 1 electron in it. And now when you look at nitrogen, Hund's rule is clear. The 1s and the 2s are full, 1 electron up and 1 down in each. But when you get to the 2p's, which all have the same energy, then each will have 1 electron before you start putting 2 into the same orbital, and they'll all have the same spin. So this puts the spin at +1 half. And so this is going to show us a simpler way to write it. So the electron configuration for neon, because it has sodium, sorry. For sodium is a 1s2, 2s2, 2p6, 3s1. If you look at the periodic table, that means sodium has 11 electrons. And it shouldn't say, the neon only goes up to the 2p6. So when it says the neon configuration, the 3s1 shouldn't be included in their squiggly bracket there. So we're going to write that as shorthand. We're going to write it as the last inert gas that was filled. So neon is on the far right-hand side. And so the 1s2, 2s2, 2p6 is the shell for neon. And then outside of that, you have a 3s orbital with 1 electron. We're going to call this the inner shell electrons, and the 3s1, the outer shell, or the valence electron. And so it's easier to write the shorthand notation, but it also gives you more information. As soon as a shell is filled, so as soon as you get to the far right-hand side of the periodic table, neon is really stable. The inert gases don't react. And so they're not going to be the electrons that are important for understanding why ions form or why covalent bonds form. It's that 3s orbital or 3s electron that's going to determine the chemical properties of sodium. So for phosphorus, it's the same thing. Shut the window, it's getting noisy. You have the neon inner shell again. And then now your valence electrons are 2 electrons in the 3s and 3 electrons in the 3p. For potassium, you've gone down a row. And so now the last inert gas on the periodic table, so have your periodic table out here, is going to be argon. And then it has a 4s1 outside of that. So the shorthand notation will be argon instead of neon, because that's the last inert gas configuration. And then it has 1 valence electron in the 4s orbital. Okay, and this one, just another example, argon. And then you have 3 outer shell or valence electrons. So there are some anomalies. We'll talk a lot about these. So there's something very stable about a half-filled d or a filled d orbital, or set of orbitals, I should say. So when you look at chromium, you'd think it'd be argon 4s2, 3d4 if you're just looking at the periodic table. But what actually happens is one of the electrons in the s orbital goes into the d subshell, so that each d orbital has 1 electron in it. So a half-filled subshell for the d's is more stable than the configuration on the left-hand side. Copper has a similar situation. It, you'd think, would be a 4s2, 3d9 for the valence electrons, but having a full d subshell is more stable, so it's going to be a 4s1, 3d10. So this is a table that comes out of your book. You can look at it, gives the electron configuration for each of the elements. And this is something you probably want to color on your periodic table. Which region of the periodic table is filling which orbitals? So the first two columns or groups are filling s orbitals. That middle transition state or transition element region is filling d orbitals. The far right, you're filling p orbitals. And at the bottom, those really should be plugged in where that black line is in the periodic table, but it would just make the periodic table too long, so they pull them out at the bottom. But you're filling f orbitals in those ones at the bottom. I don't really think this summarizes anything I haven't already said. So when we look at the periodic table and look at that idea of atomic radii, the size of the atoms that we looked at as a trend that was noticed on the very first slide, you notice that things get bigger as you go down a group, but they get smaller as you go from left to right. So you're adding electrons from left to right, but the atom is getting smaller. And it's because the Z effective is getting bigger. So the valence electrons are going to be attracted more to the nucleus because they shield each other more when they're in the same period. And I'm going to go back to the set of p orbitals so that we can talk about that quickly. So if you think about the p orbitals, so if these three orbitals are in the same period, so let's say that they're 3 p orbitals, if I put an electron into the orbital that's on the x-axis, and then I want to put one in as I go up an atomic number on the y-axis, those two orbitals are perpendicular. So the electron that's in the p orbital on the y-axis doesn't see the electron that's in the orbital on the x-axis when it looks towards the nucleus. And so the effective nuclear charge is going up. And so that means that the electrons are held tighter to the nucleus. So when you look at that very last slide we were just on, that says the effective nuclear charge goes up as you go across the period, and therefore the atomic radius goes down. So, but then as, well, we'll talk more about this. This concept I like to draw a little more visual on the board. So trust me, we will talk more about it when we're together in class. So that's all of chapter 5. And chapter 6, we'll just use what we've just learned about electron configuration to understand more trends. So not just atomic radii, but ionization energy and electron affinity. And so we'll just be applying what we did in this chapter.